Yeah.
I'm right here. And I'm happy to present our work on robustness and resilience of cities around the world. These are my colleagues, and co-authors. Javier Bosque actually was with us and he left recently to join his home city in Catalonia. So urban resilience actually has attracted lots of attention in the recently actually, and some major organizations like United Nations and Rockefeller are looking into this problem and trying to help actually cities to be more resilient. Recently, Miro and other and its authors actually have numbered more than 25 definitions of what urban resilience is based on the different topics and domains actually where it applies, like engineering science, environment science, and so on and so forth. So these are like two examples of like definitions of what is urban resilience. So one of them is like capacity of an urban area to confront uncertainty and or risk, and second one is the capacity of a system to recover its initial state after the shock, right? In the context of the Rockefeller Foundation program, which is called 100 RC or 100 Resilient Cities, actually, these guys are teaming up with 100 cities around the world from different continents, and they are trying to make policies actually to help cities become more resilient to different kind of shocks, like physical shocks, social and economical ones. So recently they came up with something they call City Resilience Index, which is like a way to measure how resilient is a city. All right, so this index actually has 4 different dimensions, which are the leadership and strategy, health, well-being, economy and society, and society, and finally infrastructure and ecosystems. And we are mainly interested in the infrastructure and ecosystems problem. So basically this one is broken down into like 3 different dimensions or goals. The first one is reliable mobility and communication, effective provision of critical services, and finally reduced exposure and fragility. Now, because we wanted to come up with a systematic way to measure this kind of index, we wanted to use data or like layer and infrastructure that is common to all the cities that are part of the study. And this layer actually is the road networks of the different cities, right? Now what we did, we tried to map each of the goals into like a technique that we master in computer science, and we try to automate actually the process of computing that metric. Now the reliable mobility and communication actually is mapped into like random failure in network. So imagine that you have this road network and you just ran like random failures on different edges, and you see how reliable is the mobility of people actually in the city. The second goal, effectiveness provision and critical services, is mapped into reachability of services. So imagine you have a graph and you want to like measure how accessible are different services from different points of the city. And finally, in order to reduce the exposure and fragility, we assume a case where someone actually targets the most important parts of the city and see how does the city react to those kind of attacks. Now, in this study, actually, we started by considering 50 different cities from different continents, and we added actually some cities that were not initially included in this in the Rockefeller program, and these are like mainly cities from Middle East where we are based. The first step in this work is to create the road network of the different cities, right? So we went to OpenStreetMap, we collected shape files of different cities, and then we came up with a heuristic that has like 4 different steps in order to create the road networks. So for us, road network is a directed graph where nodes are intersections, and then edges are road segments that link the different intersections. You will find like details of this heuristic and different steps actually in the paper. But yeah, we start like from different paths. Actually, each path is like a sequence of nodes. Each node has like a unique ID and a geolocation coordinates, latitude and longitude. And then we try to identify the most relevant nodes in each path, and we find like the intersections. And finally, we prune and remove the nodes that are useless, the ones that have like degree of 2, to finally get something meaningful. And these are like 2 examples of how the road networks look like actually, produced by matplotlib in Python. And then we computed like some statistics for different road networks. So some of them are pretty much big, like Los Angeles, for instance, has over 500,000 nodes, and it's pretty much long in terms of like length in kilometers. It's more than 113,000 kilometers. We have average degree, meshness, and organic actually that are measures to see what is the structure of the network, right? So meshness, for instance, is a score between 0 and 1. So if you are at 0, that means that your network has like tree-like structure. And if it's 1, you have like complete graph. But because like road network are planar graphs, generally the meshness score is very low. Now for the robustness. Basically, the network robustness has long tradition in complex systems and applied physics, where people studied like robustness of different types of networks, like random networks, and so on and so forth. And usually they use the percolation theory actually in that. So the idea of this percolation theory is to have a graph and start removing edges or nodes from the graph, right? And see at which time actually the graph splits into two parts. Now, if we are removing nodes, we call this side percolation. If we remove the edges, we talk about bound percolation. And in our case, we're interested in the bound percolation because it's more realistic actually to the traffic, where usually what gets close is like road segment, rather than intersection. Now, in this bound percolation, we can identify two types of attacks. We have what we call failures that are random removals of edges from the graph, right? And this approach actually is probabilistic because it's random, basically. So we had to run this kind of process like 100 times for each city and then average the results. The second scenario is targeted attack, in which case we first identify the most important segments of the network by looking at their centrality, for instance, like between the centrality, and then we target those edges and we start by removing them first. This is deterministic, but it has like shortcoming, which is the fact that it's very hard and time-consuming to compute between the centrality of large graphs, right? So we couldn't actually run this experiment for some of the large cities that we have in the study. And our assumption is, of course, that some cities might react differently to these two different kind of attacks and failures and attacks, sorry, based on the shape of their road networks. Now the approach is very simple. So we start based on the graph. We start by like graph. We compute the size of the GCC, giant connected component, and the second largest connected component, and then we iteratively remove edges from the graph, right, based on one of the two approaches that we have. Then we report like the new size of the GCC and new size of the second largest connected component. At the end of the process, when the two like GCC and SLCC actually have the same size, we try to identify the percolation threshold, which is found at the point where the second largest connected component maximizes. And let me just explain this through an example. So this is a typical graph that we have usually in percolations. Here we have the percentage of removed edges. Here we have the size of the components like GCC and SLCC, yeah. In blue, I'm reporting the size of the giant connected component. In red, I'm reporting the size of the second largest connected component. So as we remove edges, we see that the size of the giant connected component actually falls down, and then at some point, actually, at this point, we have like drastic fall, right? An important one, sharp one, which tells us that percolation has happened there. And this is like the percolation threshold, and it corresponds in this case actually to around 27% of the removals. Now what we do, we run this process for all the cities that we have 100 times, and then we average actually the score that we observe. And this leads actually to get something like this. Like this. So here we are reporting all the cities with the different percolation thresholds that they have. So the higher, the better, of course. The color code, I don't know if you can see it, but red city, actually red color is for like North American cities, yellow is for Asia, blue is for Europe, red for Oceania, and then black for Africa. We have the two types of attacks, so the random failures and then the targeted attack. What we saw like across all the cities is that the random attacks actually, in the scenario of targeted attacks, the percolation happens very early, right? After removing like very few number of edges, while more of the cities actually have decent percolation threshold for the random failures. Now, interestingly, what we observed also is that some cities actually are very vulnerable to targeted attacks. So for instance, Mandalay in Myanmar actually is, unfortunately, you can't see everything here. But yeah, I mean, this city, for instance, which is really vulnerable to targeted attacks, was the most robust city in terms of random failures. And this happens actually when you have a city with a very weak or like single failure points, right? If you have like city that has like two parts and then these two parts are linked by a bridge, then if you target that bridge, the city falls down and splits into two parts. Now in terms of resilience, yeah, I had like this kind of cool definitions to to distinguish like robustness from resilience, robustness is how much you can take before you fall down, basically, how robust you are, right? But then resilience is how long does it take you to recover, to stand by again, or how can you sustain when you are under attacks? How much can you sustain? So in our study, what we do, we try to look at the city and see whether the city can keep servicing its population even after it falls down. So we got data from like an open platform, Foursquare, for all the cities that we had in the study. And then we mapped actually these locations into different categories, right? We defined 10 different categories like medical centers, transportation and travel, and so on and so forth. And then we assign each location to its closest node or intersection in the graph. Now what we do, we compute the service availability or distribution before and after percolation, and we compare how we compute how much services are still reachable actually to the population. Let me just go to this one actually for the results, where I take like 3 different cities from 3 different continents. In green I have New York, in yellow I have Amman from Jordan, and then the red one is for London. And for each city, we report the amount of available or reachable services in different categories, right? So medical centers here, we have travel and transportation here, residence, food, nightlife, sports, art and entertainment, and so on and so forth. Now the observation is the following. New York, for instance, is a very resilient city because it preserves almost 80% of all its services even after the failure, after the percolation. A city like London, in the contrary, is a very vulnerable one because it lost actually almost 70% of its different services at percolation time. And then you have a city like Oman, which is kind of in the middle. Now, what we think is that this happens actually, the bad behavior of London means that the services are not well distributed in the city. So this might happen because some services are concentrated in some region, and if that region got disconnected, then people cannot access it anymore, right? While like city like London, maybe like New York, sorry, has more well distributed services, geographically distributed services. So for the future work, we are right now working on dynamical robustness. So what we presented and what we worked on in this paper is called topological robustness, because we looked at the actual topology of the network, and we were looking at what time actually the network splits into 2 parts. Right? It physically splits into 2 parts. Now what we are looking at is the service that is provided by that topology, which is transportation. So we run the percolation and we compute at each step the congestion level that is generated by the removal of the link. And what we think is that the dynamical robustness might happen, dynamical percolation might happen before the topological percolation, which means even if your network is still connected, it might happen that people cannot move in the city because of a very high level of congestion. The second axis that we are also looking at is the multimodal robustness, where we are trying to model the city as in multi-layered way with a multiplex. We are focusing for now on transportation layers, so we'll have like metro layer, road layer, buses layer, and so on and so forth. And then we run the percolation on different layers, on different edges of different layers, and see how does this impact actually the whole transportation service provided to people. Thank you so much.